Look at this sentence right here. If you write this in your Cambridge IGCSE Physics 0625 exam, you are going to drop an entire grade boundary. Instantly. No fluff, no warm-ups today. We are jumping straight into the single most painful, invisible mistake students make with electric charges. You think you know how friction works? Think again. Today, we are decoding the ultimate electric charge trap.
Okay, so here is the exact trap. I want you to read this seriously flawed answer. The strip became charged because it gained positive charges from the cloth. Now, you might look at that and think, well, a transfer happened. What's the big deal? The big deal is that it literally costs you the entire question. It tells the examiner that you completely misunderstand the fundamental model of the atom. Listen closely. Positive charges do not move in these solid materials. Period.
And honestly, the bleeding doesn't stop there. These tiny, microscopic errors, they are these silent killers of your top band marks in practical data questions. We see students losing marks left and right because of vague explanations, forgetting to write their units, rounding their numbers way too early in a calculation, swapping their independent and dependent variables, or writing conclusions that literally have nothing to do with the data they just collected. You can know all the physics in the world, but if you make these structural errors, your knowledge simply won't translate to marks.
This right here is exactly why your ordinary revision fails. Just memorizing a phrase like charges repel is nowhere near enough to secure those high-level practical investigation marks. The examiner isn't just checking if you memorized a textbook fact. They want to see if you can apply scientific reasoning to actual empirical data. Figuring out what they want is kind of like learning a secret language.
Okay, let's dive into this. To beat this trap, we're going to use a repeatable 4-part framework to build a top-band answer. I like to call it the rubric decoder. First up, you identify the core concept. Second, you extract the evidence or data straight from the practical. Third, you apply scientific reasoning to connect those two together. And finally, and this is the absolute kicker, you translate it all into exact examiner wording. Let's run this framework on the electric charges practical right now. Step 1 is the concept. To beat the trap we talked about earlier, you have to nail the precise definition of an electron. It's a particle carrying a negative charge that may be transferred by friction when materials are rubbed together. This is the ultimate antidote to that flawed answer. It is the electrons that move. If a material gains electrons, it becomes negative. If it loses them, it's positive. The protons, the positive charges, never ever transfer during this experiment.
Right, let's set the stage for step 2, the evidence. To gather that evidence, you really need to wrap your head around the physical apparatus used in this specific Cambridge setup. We are dealing with polythene strips and cellulose acetate strips. We've got a cloth to generate friction by rubbing. We suspend our strips using thread and a little paper stirrup hanging from a retort stand. And finally, we have the ultimate detection tool, the gold leaf electroscope.
So, when we actually put this apparatus to use, highly predictable transfers happen. Rub a polythene strip with a cloth, and the friction causes it to gain electrons. That gives you a negatively charged strip. But switch that out for a cellulose acetate strip and rub it with the cloth. It loses electrons to the cloth, making the strip positively charged. The friction is what provides the necessary energy for this entire electron transfer.
Now wait, before we even look at the interactions, there is a crucial, absolutely vital practical method detail you cannot ignore. You must ensure the suspended strip in that paper stirrup is completely stationary before you bring up the second charged strip. Examiners love to test this. If that strip is already swinging around, you can't accurately tell if its movement is caused by an electric force or if it's just leftover kinetic energy from being bumped. If it's swinging, your data is completely invalid.
Okay, now for the scientific reasoning. When we map out our empirical evidence, a totally clear pattern emerges. If you bring a negative polythene strip close to another negative polythene strip, they repel, they push apart. But bring that same negative polythene strip close to a positive acetate strip, and they attract. This empirical data confirms our core scientific reasoning. Like charges repel, and opposite charges attract.
Now in a moment, I'll show you the exact examiner clue for the gold leaf electroscope that changes your answer completely. But first, you need to understand the wording trap that makes that clue absolutely essential. Most students fall right into this trap, and it is brutal.
So, here is your spot the error challenge. Read this flawed hypothesis taken straight from a real exam paper. The polythene strip got a charge from rubbing, so it made the other strip move away. What's wrong with that? Why does it bleed marks? Well, it's horribly vague. Saying it got a charge doesn't explain how the charge moved or what type of charge it is. And made the other strip move away? That completely ignores the required scientific terminology for the forces at play.
Let's put this together using our rubric decoder. Let's look at the side-by-side transformation. On the one hand, we have the weak, vague answer, got a charge from rubbing, made it move away. On the other hand, the top band answer says, electrons transferred by friction, like charges repel. See the difference? Instead of got a charge, we specify what moved and how. Instead of made it move away, we state the exact scientific law. This right here is how you make your exam answers completely bulletproof.
So, the crucial point? It all comes down to this specific phrase: electrons transferred by friction. Whenever the exam asks you to explain how an insulating material becomes charged, the examiner is actively scanning your paper for these exact words. They don't want positive charges moved, they don't want it rubbed off, they want electrons transferred by friction.
All right, let's close that loop from earlier about the gold leaf electroscope. While the paper stirrup setup is brilliant for demonstrating forces, the electroscope is the ultimate piece of kit for this practical. It physically detects the presence of a charge. Plus, it goes a step further. It lets you distinguish between good and bad electrical conductors just by observing how quickly the charge dissipates when a material touches its cap.
Before we wrap this explainer, let's run through a quick write-your-own-answer checkpoint. Make this a habit. When you finish a practical data question, ask yourself, am I using the correct physics terminology, like electrons and friction? Is my conclusion actually backed up by the data in my table? And finally, did I check the reasonableness and the safety of the practical?
Oh, and speaking of safety, here is a ridiculously easy mark that people always forget. If a question asks you to evaluate the safety of the static electricity investigation, the source material explicitly notes, this practical presents minimal risk. That's it. Knowing when to confidently state that a hazard is minimal is just as important as spotting a major explosion hazard in a different experiment.
But here is where things get seriously dangerous. You now know exactly how to explain charge transfer perfectly. But what happens if the exam paper suddenly pivots? What if the electroscope detects a charge that causes a physical force, and you have to figure out if the command word is asking you to just explain that force, or mathematically calculate it using Newton's laws, friction and momentum? If you misread the command word, your totally perfect explanation will score you a 0.
That massive unresolved problem is exactly what we are decoding in the next part of this series. You simply cannot afford to lose marks just because you misread what the examiner was commanding you to do. To unlock that next code layer, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Jump into our next explainer right now to master the exact command words that decide your final mark band. The real question is, do you want to just understand physics, or do you want to prove it to the examiner? See you over there.